So as we got here maximum boost for quantum cat swarm optimization algorithm, in next video we will discuss this algorithm, and we will also try to cover other algorithms in upcoming videos. In this video we will discuss soft computing module 2, that is about neural networks. In previous video we discussed soft computing module 1, that is about fuzzy logic. Now we will discuss module 2, that is about neural networks, and we will cover certain topics from this module. Here you can see the topics covered in this video. First, basic about neural networks, artificial neural network, mathematical models, basic terminologies. Then we have one problem to calculate the net input to the output neuron, different types of networks, single layer, multi-layer, single layer network, multi-layer networks, activation function. Then we have another problem to calculate the output of neuron Y from given network, perceptron network, and the last one, Adeline, its training and capabilities. So first we have basic of neural networks. As we know, artificial neural networks are inspired by human brain working. Human brain basic element is neuron, and human brain is comprised about 10-100 billion neurons. They provide us with our abilities to think, remember, even we can learn from our past experiences. So like that we have artificial neural network that is inspired by human brain working. Here you can see this is the mathematical model of artificial neural network, and here you can see this is the biological network. Like biological network, artificial neural network is also composed of large number of highly interconnected processing elements. Here processing elements also known as neurons, or we can say nodes or units. These neurons are organized into layers, and here we have different types of layers: input layer, hidden layers, and output layers. So next question is how layer is formed. A layer is formed by taking a processing element, that is neuron, and combine it with other processing element. So when layer is formed, input can be connected to these node with various baits. You can see we have baits that result into series of output. Each neuron is connected with other by a connection link, and each connection link is associated with baits which contain information about input signal, and neural network can use that information to solve particular problem. So here you can see we have neurons. They are connected with each other using connection links, and you can see here each connection link is associated with bait which contain information, and neural network can use this information to solve specific problem. As you can see in the biological network main parts, we have cell body, axon, dendrites, nucleus, synapses. Like that you can see here relationship between biological and artificial neuron. Here in artificial neuron we have neurons instead of cells. We will use baits instead of dendrites. We have net input instead of soma, and we have output instead of axon. Here we have neuron, that is also known as processing elements, nodes or units, and we have different layers in the artificial neural network architecture: input layer, hidden layer, output layer, that we will discuss in detail in the upcoming slides. You can see here this is the mathematical model for the artificial neurons. Here we have input layer, and here we have different neurons in the input layer, and here you can see with each connection link we have baits associated which contain information that neural network can use to solve any problem, and then we have output. So we can calculate net output using this. Here you can see x1 w1 plus x2 w2 plus x2 w3 plus x3 w4 up to xn wn. So here it is the sum of xi wi. Here I is the ith processing element. So we can calculate net output using this. Next we have a problem. Here we will calculate the net input to the output neuron. Here you can see this is the output neuron y. So here you can see in this figure we have given 3 input x1, x2, x3, and the value we have for x1 0.3, for x2 0.5, for x3 0.6, and then we have weights associated with each connection link: w1 0.2, w2 0.1, w3 minus 0.3. And using this formula we can calculate the net output. So here we have given 3 input and weight associated. So net output can be calculated as x1 w1 plus x2 w2 plus x3 w3. Put the values here. x1 value we have 0.3, w1 0.2, x2 0.5, w2 0.1, x3 0.6, w3 minus 0.3, and we got the output value, that is minus 0.07. So this is the final value we obtain for the output neuron, that is y. Now we have basic terminologies related to artificial neural network that we will discuss one by one. First we have weights that we already discussed. We have weights associated with the connection links. Then what is bias, threshold, learning rate, momentum factor. So first we have weights. So as we already discussed, in artificial neural network, each neuron is connected to other neuron by direct communication links, and each link associated with weights, as you can see in the figure. So here we are using a matrix, that is weight matrix. Weights contain information about the input signal, and this information can be used by the network to solve specific problem. Now we can represent the weights in terms of matrix. We can call it weight matrix, or we can also call it connection matrix. So here you can see we have n processing elements, 1 to n, and each processing element has adaptive weights. You can see here we have weight matrix w1, w2, that is the weight associated with the neuron, w2, you can see this is the weight matrix, also known as connection matrix. Next we have bias. Bias has its impact in calculating the net input. Bias is included in the network by adding an element, that is x0 is equal to 1. Next we have threshold, that is value based upon which final output of the network may be calculated. Here you can see it is denoted with theta, and based on this we can calculate the net output, that is the final output. Next we have learning rate, that is used to control the amount of weight adjustment, and learning rate is denoted by alpha. Learning rate ranging from 0 to 1, that determine the rate of learning at each step during training. The last one we have momentum factor. We can make convergence faster by adding momentum factor to weight updation process, and this is generally used in backpropagation networks. Now you can see we have next problem, that is obtain the output of the neuron y using this network, and here we will use activation function to calculate the output for the neuron. So we are using here activation function. Here we are using two activation functions, binary and bipolar sigmoidal. But first we will see what is activation function. So first we will see what is activation function. After that we will solve the problem. Activation is applied to the each node in the layer of the network, and it is applied over the net inputs to calculate the output for the artificial neural network. Here we have different types of activation functions: identity, binary, bipolar, sigmoid, ramp, rectified, softmax, that we will discuss one by one. First we have identity function. It is a linear function. It is a linear function that can be defined as fx is equal to x for all x. You can see in the figure it is represented as, in the identity function, the output remains same as the input because it is a linear function. The next one we have binary step function that we can define using this. Fx is equal to, if x is greater than or equal to the threshold value, then value output as 1. If the x value is less than threshold value, then 0. You can see the representation of this function here, 0 and 1. You can see we have values 0 and 1 for this function. Theta, you can see the theta, that is the threshold value. This function is most widely used in single layer network to convert net input into an output, that is using binary, either 0 or 1. Next we have bipolar step function that we can define using this. There is only one difference. Here we have 1 and 0. Here in bipolar we have 1 and minus 1. You can see the difference. In this we have 1 and 0. Here we have minus 1 and plus 1. Bipolar step function is also used in single layer networks to convert net input to output, and here we are using bipolars minus 1 and plus 1. So we have two types of sigmoid functions in the problem that we are going to solve. In that problem we will use these two functions to solve the problem. So here we have first type, that is binary sigmoid function, that we can define using this. Fx is equal to 1 divided by 1 plus e raised to power minus lambda x. Here you can see the representation of this function, and this one is widely used in the backpropagation networks. Next one we have bipolar sigmoid function that we can define using this. The only difference, here we have 1 divided by, here we have 2 divided by, and it is represented as this. Now we have ramp function that we can define using this. 1 if this condition is true, x if this condition is true, else 0 if this condition is true. So now we will go to the problem using activation functions as binary sigmoidal and bipolar sigmoidal, and you can see here we have bias. So you can see we have given 3 input, x1, x2, x3, and we have given 1 output, that is y, and you can see the weights associated with each connection link. So you can see now we have input x1, x2, x3. Value for x1 we have 0.8, value for x2 0.6, x3 0.4. Then we have weights associated with the links, w1 0.1, w2 0.3, w3 minus 0.2, and you can see the bias we have. So value for this we have 0.35. So the net input to the output is so the net input to the output neuron is calculated using this. So here we will add bias plus the same formula we used to calculate net input. So value for b, that is 0.25. So here it is b plus x1 w1 plus x2 w2 plus x3 w3. Put the values here. B value, that is 0.35, x1 0.8, w1 0.1, x2 0.6, w2 0.3, x3 0.4, x w3 minus 0.2. Put the value here and we got the value for this, that is 0.53. After that we will apply activation functions. Using activation functions we can get the efficient output. Here we have two activation functions, first binary and bipolar, binary sigmoidal and the bipolar sigmoidal function. So here we have first, that is binary sigmoidal activation function. Net input we obtain, net input to the output neuron we obtain here 0.53. First we will apply the binary sigmoidal activation function. You can see we can define this function using this. So here we will put the value, this here and we got output for this 0.625. Next, we will do this for the bipolar sigmoidal activation function. Put the value again here. You can see the define the function, then put the value this time we have again 0.53, changes here just 2, and in previous one we have 1, and the output we got here 0.259. So next we have different types of neural networks: simple artificial neural network, single layer, multi-layer, then we have recurrent, single and multi-layer. So first we have simple neural network. You can see we have first simple neural network. We have 2 input, then 2 weights associated with it, and then giving 1 output, that is y. So we have 1 input layer, there is no hidden layer. So here you can see, and we can calculate the net input for this simple artificial neural network using this x1 w1 plus x2 w2. So y is equal to x1 w1 plus x2 w2. Next we have single layer feed forward network. So about feed forward network, so we can call a network feed forward network if no neuron in output layer is an input to the node in the same layer. So here you can see this is single layer feed forward network. We have input layer, we have input layer, we have input neurons, and we have just output layer, and here we have output neurons, and you can see weights associated. Next we have multi-layer feed forward network. Multi-layer feed forward network is formed by interconnection of several layers. For example, you can see here we have different hidden layers. Right now you can see here we have multi-layer. So here you can see we have hidden layers between input layer and output layer. Hidden layers are internal to the networks. It has no direct connection with the external environment. In artificial neural network, there can be 0 or several hidden layers. It depends on the network complexity, and you can see we have 1 output layer. Next we have single layer recurrent network. Recurrent networks are feedback networks with closed loops. Now what is feedback network? Feedback network output can be directed back to the input to same layer node. Like you can see here, the output can be directed back to the same layer. So here we have single layer recurrent network, that is a feedback network with the closed loop, and you can see. Next we have multi-layer recurrent network. Now we have perceptron, that is the simplest form of neural network. It take multiple binary inputs 0, 1, -1, and here you can see different operations. It contain input layer, hidden layers, output layer, activation function, weights, weighted sum, many more. And for any perceptron we can calculate the output using this. Here this is the activation function that is defined as f of y, and here it is defined as, using this we can calculate the output for any perceptron network. Here you can see we have given this simple perceptron network. So perceptron network consists of 3 units, or we can say 3 layers, that is input layer, hidden layer, and the output layer. Here you can see we have sensory input. They are connected with the fixed weight, have values either 1, 0 or -1. They are randomly fixed. And we have binary activation function used in the sensory unit and associator units. And you can see here we have the response unit. The response unit have activation of 1, 0 or -1, and the binary step with fixed threshold theta used as activation. The weight will be adjusted on the basis of the learning rule, and if error occur for particular pattern we can fix using this. If no error occur, there is no weight updation, and hence the training process may be stopped. So here you can see in this equation we have t, that is the target value, that is either +1 or -1. Alpha, here you can see alpha we have, this is the learning rate. And you can see here this is the single classified perceptron network. Here we have bias, and then we have inputs and weights associated with the connection links. Next you can see here we have flowchart for the perceptron network with single output. So here we will start with the bait initialization. First we will initialize the baits and the bias, and for simplicity we can set the value 0, and we will also set learning rate here, learning rate alpha 1 for simplicity, or you can define its value 0 less than alpha less than equal to 1 in the range 0 and 1. Next you can see here xi is equal to si. The input layer containing input units is applied with identity activation function, that is linear. Whatever input we will give, it will give the same output. After that we will calculate the net input y, and using this equation we can calculate the net output of the network. So now we will apply the activation over the net input calculated to obtain the output. So here we obtained the net input. Now we will apply the activation function to obtain the output. So now to calculate the output of the perceptron, we will use this activation function. Here we will use this to calculate the output. Next we will adjust the baits and bias. Now you can see we have a condition here. So we will compare and check the value of the calculated output and the desired output. So here you can see we'll compare this value with the target value. So if this condition is true, then we will calculate using this, else we will calculate using this. After that we will train the network until there is no weight change, and when the stopping condition is met for the network, and we will repeat the loop until the stopping condition is met. Next we have multi-layer perceptron. It is also a type of artificial neural network that consists of multiple layers of neuron, and it can have one or more hidden layers. Here we have different components for this: input layer, output layer, baits, activation function, hidden layers. Next we have Adaline, that is adaptive linear neuron. It is a single layer neural network that perform linear regression. We have different key features for this: cost function, weight update rule, training with gradient descent, linear activation function. Here you can see this is the simple model for this. For the training process, first we will initialize the bait, then we will compute the baited sum of input, compute error for each training, then update baits using the gradient descent rule. We repeat the step up to B to D. For the capabilities, and here for the capabilities we have baited sum, it is linear regression, sensitivity to the input scaling. Recurrent network, that is artificial neural network designed for the sequential data processing. Recurrent neural network, we have recurrent connections, sequential processing, hidden state, vanishing gradient problem, and architectural variants. So here we cover certain topics for this video. In next video we will try to do this with examples for the neural network, how it is working step by step. So that's all about this video. If you have any questions, you can comment below, and thanks for watching this video.